approximately 100 million years ago. A large, icy satellite approached Saturn too closely. The gas giant's extremely powerful tidal forces shattered it into trillions of small bits. Obeying the overwhelming physical laws, these bits gradually spread out, embracing the planet in a primary ring. It was roughly 1,000 times more massive than Saturn's today's rings. Millions of years have passed since the time of the disaster. Since then, some part of the destroyed satellite's fragments was swallowed up by Saturn without a trace. Other debris bombarded the surfaces of its multiple satellites, or else left the environs of the gas giant altogether. This is one of the most well-grounded scientific hypotheses today that account for the origins and evolution of Saturn's rings. Even after hundreds of years of observations, this tremendous structure in space still hides a lot of secrets. Saturn's rings do not have a clear-cut border. The width of their visible part is about as much as 280,000 kilometers, although there are thinnest clusters of dust and rarefied gas beyond these borders. These structures' diameter reaches 16 million kilometers, according to some estimates, although they cannot be seen from the Earth on account of their extremely low density. In spite of the impressive dimensions, the total mass of the ring system is quite small by space standards and is estimated at 3 times 10 to the power of 19 kilograms, which is about 2,000 times lighter than the Moon. Solid objects account for only 3% or so of the structure's overall volume, with the rest filled with rarefied gas and cosmic dust. The disk surrounding Saturn is conventionally divided into several large rings. However, a rather powerful optical telescope will reveal each of them to be clearly made up of a large number of thin circles separated by narrow gaps. These gaps form due to the gravitational influence of both the planet itself and its many satellites. Some of them are as much as several hundred kilometers wide. Even though Saturn's disk reflects several times more sunlight than the gas giant itself, some rings are next to impossible to see. For example, the D ring, the closest to the planet, which consists of tiniest water ice crystals and frozen methane. Its upper border is posited to be located 16,500 kilometers above the planet's conventional surface. As for its inner part, the ring has no clear-cut border and gradually fuses with Saturn's atmosphere. Next to it is the brighter and more massive C ring, which is approximately 17,500 kilometers wide. It is comprised of space objects measuring up to 2 meters and which make up just 0.033% of the disk's overall mass. The brightest and most outstanding part of the disk is located further and is designated the B ring. It begins roughly 34,000 kilometers above the surface of the gas giant, and its width reaches 25,000 kilometers. The thickness of the larger part of the ring does not measure over 5 to 10 meters, while its outer part forms a vertical rim towering up to 2.5 kilometers high. The outermost visible ring of Saturn begins 64,000 kilometers above the planet's surface. It is roughly 14,600 kilometers wide, harboring not only comparatively large ice bits of 10 meters and more, but some satellites as well, such as Pan, Daphnis and others. The existence of such large objects may prove the theory of ring formation following the destruction of the ice satellite. Alternatively, they may have formed at a later time as a result of smaller fragments colliding and merging. Beyond this part of the disk, there lie the almost unobservable F, G and D rings, which formed from cosmic dust and rarefied gas. It goes without saying that most of Saturn's large satellites actively interact with the rings. Traveling as far as 179,000 kilometers away to the region of the so-called E-ring, the celestial body dubbed Enceladus is to be found. With a diameter measuring just 500 kilometers, it does not qualify as one of the gas giant's largest satellites, but it stands out for other reasons. The point is that Enceladus is one of the few celestial bodies in our system where there are clear manifestations of cryovolcanic activity. Analysis of the observed emissions proves that there is an ocean of liquid water under its surface. Mathematical modeling shows that its temperature measures from 45 degrees Celsius below zero in the upper layers to 0 degrees at the bottom. Due to a high content of dissolved salts and ammonia, the ocean does not freeze over even in sub-zero temperatures, with the icy shield about 2 kilometers thick covering and thermally insulating it. The celestial body's surface temperature is about 75 Kelvin or 198 degrees Celsius below zero. Its atmosphere is extremely rarefied and is 91% water vapor. Other elements making it up are nitrogen, carbon dioxide and methane. Powerful geysers that erupt from time to time through cracks in the icy crust of the satellite regularly supply its atmosphere with chemical elements, but the celestial body's weak gravity is not enough to prevent the atmosphere from floating away. The upper region of the atmosphere is constantly losing some amount of particles that go to sustain the E-ring. On the other hand, Enceladus constantly captures material from the space around it, thus ensuring its peculiar chemical balance. It is known that geyser activity of this celestial object depends on its orbital movement. It is likely that Saturn's tidal forces deform the satellite's icy shield, causing it to crack in multiple places and to erupt. It is also known that the cryogeyser's emissions contain elaborate organic molecules, which may mean that the conditions in the subsurface ocean may hypothetically be favorable for the genesis of biological life. Also, the gas giant's fifth largest and most massive satellite, Tethys, can be seen approximately 300,000 kilometers away from it. It is peculiar for sharing the same orbit with two other celestial objects, Telesto and Calypso. They are located at the so-called stable Lagrange points, with Telesto 60 degrees ahead of the main satellite in its movement along the orbit, while Calypso, on the contrary, lags 60 degrees behind. Unlike the massive spherical Tethys, these celestial bodies are not that large and are irregular in shape. They measure roughly 20 to 30 kilometers in diameter, with their overall mass just several trillion tons, which is modest by space standards. Interestingly, modeling shows that Calypso and Telesto could not have originally formed in the same orbit with a more massive body following it, which means that they arrived to join it at a much later time. As for Tethys, it is a celestial object with a diameter measuring about 1,060 kilometers, made up of mostly water ice, with some rocky impurities in its composition. The most outstanding feature of its relief is the giant impact crater Odysseus. Its diameter measures around 450 kilometers, which is about twice as small as the diameter of Tethys itself. Its depth reaches as far down as 3 kilometers. There is also an easily noticeable chasm of enormous proportions on the satellite's surface, which is called the Ithaca Chasma. It is as long as about 2,000 kilometers. That is about a third of the celestial body's circumference and as much as 100 kilometers wide. As for its depth, it ranges from 3,000 to 5,000 meters, and the bottom is pockmarked with a great number of craters and minor irregularities of the surface. According to one of the theories about it, the Ithaca chasm formed as a result of Tethys' subsurface ocean freezing over. On turning into ice, the water expanded in size and erupted through the satellite's outer crust. Another assumption about the chasm has to do with the Odysseus crater. It is thought that the impact waves traveled across the entire surface of the satellite and caused a powerful resonance around its circumference. As a result, Tethys' crust cracked, forming this incredibly large chasm. Still further from Saturn, there lies its largest satellite, Titan, which also boasts quite a number of highly unusual features. With a diameter measuring 5,152 kilometers, it is in fact the second largest satellite in the solar system, with Ganymede holding the first place. It is also remarkable for being 5.5% bigger than Mercury. Titan is also the only satellite in the solar system with a dense atmosphere and bodies of liquid on its surface. Since Titan lies quite far from the Sun, the temperature of this celestial body is quite low at around 94 Kelvin or 180 degrees Celsius below zero. Having said that, in spite of its comparatively small mass, Titan is capable of sustaining an atmosphere which is 1.5 times denser than that of the Earth. Nitrogen accounts for over 98% of the atmosphere's chemical composition, with methane and other gases making up the rest. Exposed to solar wind, nitrogen and hydrocarbon compounds in the atmosphere's upper layers transform into more complex organic substances, which subsequently slowly settle on Titan's surface. Due to the impermeable hydrocarbon smog, the satellite's surface is unobservable in the optical range. According to the most plausible model of Titan's inner structure, there is a massive rocky core at its center, with a diameter measuring about 3,400 kilometers. It is embedded in a thick layer of exceptionally dense ice, which forms the bottom of a cool salty ocean containing up to 10% of dissolved ammonia. It is buried under a crust of water ice mixed with methane hydrate, which is many kilometers thick. In temperatures as low as that, the ice has properties identical to those of a solid substance and forms mountain ridges and elevations on the surface. As for lowlands and chasms, they are filled with lakes of liquid ethane and other hydrocarbons. Solar wind and Saturn's extremely powerful magnetic field constantly strip Titan of its atmosphere. However, its internal processes keep replenishing it, so the process of losing it may take billions upon billions of years. When the Sun hits the red giant phase, it will be capable of vaporizing the hydrocarbon haze and melt the eternal ices on Titan. After this, the satellite will become a more favorable place for the genesis of life. However, it will not happen for a while yet. Of course, Saturn's system does not end there. It contains dozens upon dozens of truly exciting objects, and occasionally delights us with new discoveries. For example, one more satellite was discovered in 2009, which lay extremely close to its planet. And in 2019, astronomers introduced the world to about 20 small celestial objects at once, which orbit the gas giant. The more we study the universe, the more overwhelming is the impression that there are likely billions of systems out there which are not less elaborate and mysterious than this one, and there is still no way to know what we will see when we finally get to observe them. Dear friends, due to a few reasons, we're not posting new videos as often as we would naturally prefer. That is why, to always keep in touch with you, we're starting a series of short 1-minute films in our Telegram. These are short, informative videos both about the solar system objects and